In this section, we're going to discuss related rates. It's the name of the section. But really, it should be called related derivatives. Derivatives are rates of change. dy dx says, how does y change with respect to how x is changing? And that gives you the slope of the tangent line. dy dt is different. It says, how does y change with respect to time? And we have other derivatives like dA dt, dV dt. How does volume change with respect to time? These are connected to real-world problems like inflating a balloon. So if you inflate a balloon, certainly you can calculate the volume of a sphere 4/3 pi r cubed. But my question would be, how quickly are we accumulating volume? How quickly is the balloon being inflated? That would be a rate of change. We need a derivative for that. A drop of oil goes on the surface of the water, and then the oil spreads out. How quickly is the area of that water being affected? How quickly is the radius of that circle growing? Those are rates of change. Now it says related rates because these rates of change, like take the oil for example, the area is growing, so that's a dA dt, and how quick is the area growing? And the radius is growing as well. That's dr dt, and that's a different quantity. Turns out they're related to each other through an equation. So we need to find these equations. We need to discover them, and we also need to use them to find out how one rate is affecting the other. So let's get started. And what I'm going to get started with is how a geometric formula relates static quantities. When I say a geometric formula relates static quantities, I'm talking about a formula for things like area. So let's say there is some oil that is spilling onto the top of the surface of water. What that's going to do, and if we look top down on the water, is the first drips go in, and then what's going to happen is the area of this circular affected region is growing. It's growing like this. Now, the first thing we could do is freeze this movie, because it truly is a movie. All of these are movies, and we're watching the area grow. Freeze the movie. Get a static picture, one frame of the movie, and this is what you'll see. When you take a photograph, you see that there's a radius, and naturally there's an area, and then we need that static formula, that geometric formula. We'll call it the static geometric formula. The static geometric formula for the area of a circle is well known to us. It's A is pi r squared. The area of a circle is pi r squared. If you know the radius, then you know the area. You can compute it pretty readily. Now, here's what I'm really interested in. How fast are we accumulating area? How fast are we accumulating area? And also, how fast is the radius growing? Now, for a problem like this where you're pouring some oil on the surface of the water, I can say that we're accumulating area. We're not reducing area. We're getting more area. I can also say that the radius is growing. It's not shrinking, but it could shrink, and that would be a different problem. So how fast? These are rates of change. Derivatives of rates of change. Pardon me. So this rate of change is dA dt. dA dt says how is area changing with respect to time. Not with respect to x, not with respect to r, or with respect to anything else. When we talk about rates of change, they are generally with respect to time, because time gives us that notion of speed, and we have speeds in the x and y direction. We have speeds of areas growing and speeds of radii growing and all sorts of different speeds. In this case, this is the speed at which area is growing. How fast is the radius growing. That would be dr dt. dr dt says, how is radius changing with respect to time? And that would be a rate of growth of radius. And that's what we saw up here. The area was growing. See, we keep getting more and more area as time progresses. But also, the radius is growing. And so the radius also has its own growth rate. But that's a linear growth rate. It's only growing in one direction linearly. Now, the real issue is related rates. That's the title of this chapter. How is this rate related to that rate? Start with the static equation. And we need derivatives with respect to time. Now, this is an equation, and you are allowed to do whatever you want to an equation as long as you do it to both sides. We choose to take the derivative with respect to time. Of the left side, we choose to take the derivative with respect to time of the right side. And let's see where that leaves us. This actually brings us back to implicit differentiation, which is the last topic we talked about. Because as you notice, when you look at this equation now, the variables don't match. The variable I'm taking the derivative of doesn't match the variable I'm taking the derivative with respect to. What happens when the variable doesn't match? Well, actually, it's chain rule. And you can think of this as a to the 1 power. And you can think of it as chain rule and 1 being the outer function. Check it off. The 1 drops down. You deduct 1 from that exponent. No change to the argument. But you got to check this guy off too. And that's going to be a dA dt. On that left side, what I got is 1 times dA dt, or just dA dt over there. Now, we talked about this from implicit differentiation. There is a shortcut here, and that is the following. If the variables don't match, take the derivative normally. Now, a is not a constant. A is area. It's changing. It's a variable. So the derivative of a variable, like x, if this was just an x, the derivative would be 1. So there it is. But the variables don't match, so you always get a singular derivative, a d variable dt in this case. So there's your dA dt. Let's move on over here. The pi is a constant multiple. We're going to pull that out front. And what's going to happen is what you really need to do is d dt, the r squared, because r is a variable, not a constant. It keeps changing on us. Well, the pi is not going anywhere, and if you want to use the shortcut, which is probably the best idea, take the derivative normally, which would be 2r, and then because the variables don't match, you will get a d variable dt. It's always singular like that. This is our first related rate problem. And now, not only do we know that area is pi r squared, I know how the speed at which area grows matches or is related to the speed at which radius grows. It's related right here. In fact, r is in there too, so that must have a bearing. Well, let's say that the area growth is, or let's say that the dr dt is known. Let's say dr dt is known for a moment. And let's say the radius of the circle is growing at a speed of 1 centimeter per second. So that's what it would look like from the center. Every second we let go by, we get another centimeter. But each time you let that second go by, what about the growth in area? Well, the first second we go from no area to that circle. Then we add all of this extra area out here the second, and that is quite a bit of extra area. And then the third second, we add all this extra area. And then the fourth second, we add these, and we'll call these annular sections of area. So each second, it looks to me like as time progresses, the area increase is getting faster. We're getting more area the more and longer we wait. The longer we wait, the bigger the radius, correct? So let's say dr dt is fixed at 1 centimeter per second. Every second you wait, the radius of the oil spill grows 1 centimeter all day long. I wonder, what is dA dt at 2 centimeters for our oil spill? And I also wonder what dA dt is later on at 10 centimeters. Now, I want you to think this through for a second. What do you think is going to happen here? When the radius is small, it's still growing by 1 centimeter per second, but the contribution of area for that 1 extra centimeter, not that much. But when you're out here at 10 centimeters, 1 extra centimeter along the outside of that circle is a tremendous amount of area. So now, dA dt has increased. We're getting more area per second. So I think that dA dt should be smaller here and larger here. Let's find out. So dA dt equals, for 2 centimeters, 2 pi r dr dt. That would be 2 pi 2 centimeters, and dr dt is fixed at 1 centimeter per second. Well, that's 4 pi, keep your units, centimeters squared per second. And I'm pretty happy about the units because that is a speed of area growth. It's centimeters squared. So we're accumulating 4 pi, or roughly 12, 13 square centimeters per second at that moment in time. So what we're doing is we're allowing the movie to progress to here, 2 centimeters, and we're saying, hey, at that moment, how quickly are we accumulating area per unit time? And we seem to be getting that much area per second at this moment. Later on, that's going to be higher, like at 10 centimeters. dA dt is still going to be 2 pi r dr dt, okay? But this time, r is 10 centimeters, and I want you to keep your units so that the units do match what they should be. dr dt is a rate of change. How quickly is radius growing? Well, for this problem, it's fixed at 1 centimeter per second. And look what happened to dA dt. It's now 20 pi centimeters squared per second. That's 5 times faster accumulating area than we did when r was just 2 centimeters. So it did sort of match our expectations. And that's a good thing to be able to do that. Okay. Let's try a different problem. Let's go 3-dimensional and let's inflate a balloon. So if we inflate a balloon, the balloon will have volume. And there's a couple of rates regarding the balloon that we could talk about, but probably the most important one will be dV dt, which is how quickly am I acquiring volume per unit time, how fast is the balloon growing volumetrically. And then inside, if you put something right in the center and you go to the edge of the balloon, well, the edge of the balloon is also moving, and that's going to be your radius growth. From the center to the edge is a radius, and therefore what is dr dt? That's the rate of change of the radius, basically, how quickly is it growing. By the way, these rates can be negative. And if we started with a balloon fully inflated and we started deflating it, dA dt and dr dt would be negative. It's a different problem. We're losing radius per time. We're losing area per time. That's a different problem. There is one more quantity we could do with the balloon, and that would be d, let's say, capital S dt, and that's the surface area of the balloon. Because as you inflate the balloon, you're getting more and more surface area. That would be a whole different problem. So what I want to do is try to relate the volume change speed with the radius change speed. Let's see if we can do that. So I'm going to look at an example in the book. They've got a great example. This is example 3, and that's worth taking a look at. So example 3 says, air is being pumped into a spherical balloon at a rate of 4.5 cubic feet per minute. Air pumped in a balloon at a rate, that means derivative, of 4.5 cubic feet per minute. So let's say cubic feet per minute. Well, let's stop there. First of all, what is that? What rate and what derivative is that? This is a volume change per minute. So that's dv dt right there. How does volume change with respect to time? That would be positive 4.5 cubic feet per minute. Every minute at this moment, we're getting 4.5 cubic feet of air. And that seems pretty reasonable for inflating a balloon, because whether it's a pump or you breathing into the balloon, more or less going to provide a constant volume of air into that balloon. I know that as the balloon gets larger, it might be harder to inflate the balloon, and maybe dV/dt goes down a little bit. But if it's a pump generally can do this. It'll pump in 4.5 cubic feet per minute the whole time through until the balloon pops, I guess. Now, let's talk about the question. Find the rate of change of the radius of this balloon. Now, the rate of change of radius is going to be very, very different, isn't it? I want you to imagine this for a minute. No math needed. Blow up that balloon with one breath. That's 4.5 cubic feet per minute. And then, the balloon starts off completely uninflated, and it immediately blows up pretty quickly, actually. That first breath, it actually grows pretty quickly. Radius grew very rapidly. I now want you to imagine the balloon is this big, okay? Put that same breath in, and the balloon barely moves, right? Barely moves. So because all that volume of air goes all along the outside of the sphere, and it moves that radius ever so slightly. So here's what I'm thinking. I'm thinking that the speed at which the radius grows will be very large when the radius is small, and very small when the radius is big. It's going to be kind of opposite. That's at least the thought. Find the rate of change of the radius when the radius is equal to 2 feet. And let's also do another one when the radius is 10 feet. Okay, first of all, rate of change of radius. What is that? That is dr dt. That's what I need. So dr dt is what we're looking for, the speed at which radius is increasing on us or growing. Here, I think we expect dr dt to be large. And here, I think we expect dr dt to be small, based on our perception of blowing up that balloon. Now, that's all good to think about, but we need that formula, right, that relates these two rates together, related rates. That's what the title of the chapter is. How does this rate relate to that rate? In order to do that, you need the static geometric equation. And for a balloon being inflated, its volume is 4/3 pi r cubed, because that is the volume of a sphere. This is the static photograph. You give me radius, I give you volume. Or, if I give you volume, you can actually give me radius as well. But that doesn't really speak about the speeds. So to get speeds, you're going to want to ddt both sides. ddt the left side, ddt the right side. And let's hope that this happens. That at the small radius, we get a big dr dt like we think we should get. And at a big radius, we get a small dr dt based on our perception of inflating a balloon. Let's hope that works. Okay. If there's one thing about these related rate problems, the variables never match. Because really none of your geometric formulas have t in it, which is like the independent variable. It doesn't ever really show up. So we're always going to be ddt'ing. The variables will never match. And that means you'll always produce these extra derivatives like dv dt and dr dt. So let's see what happens over here. The derivative of v is 1, just like the derivative of x is 1. And you will get a singular dv dt from that. Here, the 4/3 pi is just a constant multiple. That survives. And what we really need to do is take the derivative of the variable r cubed. So the 3 comes down, deduct 1 from the exponent, and wait, the variables don't match. That means you need a singular dr dt. You notice they're always singular. They're never squared, cubed, or anything like that. They're not second derivatives. They're always first derivatives. And the 3's cancel. So how does the rate of volume change relate to the rate of radius change? Apparently, we just discovered the related rate equation. So the way you get this related rate equation, again, is by ddt'ing both sides very carefully. So now, let's plug some information in. Now, this problem told us up front that the amount of air going into the balloon throughout the entire problem, dv dt that is positive. The air is going in, and it's 4.5 cubic feet per minute. We also want to know what happens when r is only 2 feet. And the thing we want is dr dt. So that's our prize. Well, I suppose you could solve for dr dt before you do all of this, and I don't think that's a bad idea. So dv dt equals 4 pi r squared dr dt. Dr dt is the very item we want, so why not solve for it? So dr dt is equal to the following. It's dv dt divided by 4 pi r squared. Now we can reuse this for the rest of this problem because it says dr dt equals, and that's what you want. Now remember, dv dt is just a speed, and it was given, in fact, it's just a number. Keep the units, by the way. It's 4.5 cubic feet per minute. Stick that right in there. For the first problem, we've got r set to 2 feet. So what's the speed at which radius is growing at that initial moment when the balloon is being inflated, when the balloon radius is small? It should be rapid. On the top, you have 4.5 cubic feet per minute. On the bottom, you have 4 pi. You have r squared. So what is that? 4.5 cubic feet per minute. That's a rate or a speed. This is 4 times 4 is 16 pi square feet. The feet cancel out and leave me with this number. And luckily, the units are correct. Now let's find out what that number truly is. 4.5 divided by 16 pi. All right, so it's 0.0896 feet per minute. Wasn't as fast as I thought. And that relates to 1.074 inches per minute if you want to multiply by 12. It's not that fast. But presumably, when the radius gets to be way out here at 10 feet, that same breath of air will not make the radius move that fast. I'm expecting it to be quite a bit slower. So let's try this again, and let's try it at r is equal to 10 feet. Okay, so that's for r equals 2 feet. When we're just starting to get going on this balloon, it's moving at about 1 inch per minute. 1 inch per minute. That's fairly slow, but man, I think it's going to slow down even more when we get to 10 feet. Now, dr dt is the speed at which radius is growing. It is calculated as dv dt, which is just a number, by the way. I've got that number, and it's over 4 pi r squared. Now, the number for dv dt, we've got it for all of the problems on this particular exercise. It's always going to be blowing air in at 4.5 cubic feet per minute. But later on, the balloon is much larger. It's got a 10-foot radius. And what do we get now? 4.5 cubic feet per minute. Keep track of your units. This is 4 pi, this is 100, and this is feet squared. The feet cancel again, which is good, because we're ending up with 4.5 over 400 pi, and the units are feet per minute, which is a nice linear unit, which you would expect for radius. So let's calculate that one and see how many inches per minute we got. 4.5 divided by 400 pi. Wow, this thing slowed down. The radius rate of growth at that moment is pretty minuscule. Multiply by 12. Let's see how many inches per minute we got. Boy, I'd say at 10 feet out, this balloon, the radius, slowed down tremendously. So that's a very good example of a related rate problem, volume and radius. Now, I've got a couple more examples here. Most of these are geometric, but I think I'd like to try one that is relating to another geometric figure, a triangle, but it's not area, it's not volume, it's something a little different. So let's do this. So what I'd like to do is look at a problem that involves an aircraft. We're going to put on the ground here a radar facility. Radar. So we take our radar facility, and what we're going to do is we're going to be looking out for aircraft like this aircraft over here. So we've got an airplane flying by right here. And we're going to call this S. And what I want to be able to do is I want to know, can I use the radar down here to determine how fast the airplane is going? Now, radar can bounce off the aircraft and tell you exactly how far away the airplane is from that facility. It can also tell you how fast it is, but only how fast it is coming towards this facility, not how fast it's going this way. If I drew a triangle right here, it would be a right triangle. And we would probably know what this leg is over here because that would be the altitude of the airplane. And let's say the airplane was at 30,000 feet, approximately, which would be 6 miles in the sky, 6 miles high in the sky. Now, this leg of the triangle would be x, and I think the Pythagorean theorem would tell us the static equation that x squared plus 6 squared should be s squared. A squared plus b squared is c squared. That's the static equation. X squared plus 36 is equal to s squared. Now, what I really want here is the speed of the aircraft moving in this direction. That's the true speed. It's horizontal speed. The speed of the aircraft in the horizontal direction only, and actually it has no vertical speed because it's level at 6 miles up, which is about 30,000 feet. So the only speed you've got is dx dt. How does x change with respect to time? The speed of the aircraft is dx dt. How does x change with respect to time? Now, there actually really is no dy dt. It's 0 because the aircraft is level. Now, two things that you can pick up from radar. One thing is radar can provide the distance, which is s. Now you see that it's a slant distance, so it doesn't give you altitude, it doesn't give you x, it just gives you s. It says the shortest distance between 2 points is this diagonal line. That's the hypotenuse. Radar also has the ability to provide a speed. But what kind of speed? Well, the speed it can provide is only how s is changing with respect to time. And I would imagine in this case, if the aircraft is flying this way, I would imagine that ds dt is getting smaller. So ds dt can be provided by the radar. So the speed of changes in s only. So ds dt could be provided, and it should be negative if the aircraft is flying towards us, and it'll be some value, some number. So there they are again, two rates. How are they related? Well, the equation, the static equation, the photograph is x squared plus 36 is s squared, ddt both sides, ddt the right and the left. The variables will never match, so this will be 2x times dx dt plus 0. This will be 2s times ds dt. Now, the prize for this one is dx dt. How fast is the aircraft moving in the horizontal direction? So let's solve for it. Divide both sides by 2x. And dx dt can be computed as follows. It'll be s times ds dt over x. So dx dt is the speed at which the aircraft is flying. That's what I really want to know. That's what a GPS would tell us. The radar can't really give us that directly. It can only say, how fast is it coming towards me along that hypotenuse? That's a different speed. We now know how these speeds are related. Let's work a problem out. So the radar reports in and says, right now, ds dt, the rate at which that hypotenuse is changing is minus 400 miles per hour. So based on the radar, it's coming at the radar site at 400 miles per hour. It's negative. The reason, again, it's negative is because the s will be shrinking. As you get closer and closer, s gets smaller and smaller. That's what would happen to a hypotenuse. The radar also reports that the current hypotenuse is 10 miles. Now remember, that 10 miles does not mean it's 10 miles high in the sky. It's 6 miles high. And that 10 miles is not x either. This is 10 miles here. With that information, can we get the speed of the airplane? Well, dx dt, the speed of the horizontal speed of the airplane, is s over x times ds dt. That would be s, 10 miles, over x. I don't know what x is, so we're going to have to do some work on that. But ds dt I do know. It's minus 400 miles per hour, and per means division. What's x? Nobody mentioned x. Luckily, we have the Pythagorean theorem that will get us our x. We can go back to the static formula. So it's still true that x squared plus 36 must always equal s squared. Therefore, x squared plus 36 is equal to 10 squared. X squared plus 36 is equal to 100. Subtract 36, and what do we have now? So this is going to be 64, and therefore X is going to be 8 miles. Normally you do plus or minus, but we're not going to do plus or minus here because there's no negative measurements for your mileage. So 8 miles, that's my X. I had to go find it using the static equation. I want you to see something. Do you notice that the miles cancel? So what's dx dt going to be? Dx dt is minus 4,000 miles over 8 hours. That would be minus 500 multiplied by 8, that's your 4,000, divided by 8 hours. Airplane is moving at minus 500 miles per hour. How could it be moving at minus 500 miles per hour, right? You'd never see a negative speed on your speedometer. So let me see why that's happening. If you take a look here at the diagram, the rate is correct. dx dt is the rate in which x is either increasing or decreasing, and x is definitely decreasing. So dx dt should be a negative speed. That's how we get things to decrease. So that is really correct for our problem. Minus is correct because of the decrease. Now the last thing I'm going to leave you with is I'd like to be able to do a related rate problem that's a little tougher. I'm not going to do the full problem, but I'm going to show you how to DDT a problem like this. Cone. You ever see those water coolers that have these cheap little paper cups like this? They actually do, and they fill them up with water, right? And you drink from them. What if you were to snip off the end? What would happen? If you snipped off the end, it would start leaking. Well, what else would happen? Several things. First of all, this is the volume in here of water, right? And you would have a dV/dt. You'd have volume change with respect to time. If it's leaking, I guarantee you that's negative. Also, as the water level goes down, what happens? Well, let's put the water level down here. Take a look at that radius here. Well, radius is shrinking. So dr dt would be the speed at which it's shrinking. I think that's negative too. Also, you have a height to your water level, and look at that. Your height is also shrinking. These are all negative when water is leaking from your cone. How do these three rates relate to each other, though? They do, but how? The volume of a cone is pi over 3 r squared h. And now we need to take probably the most difficult related rate derivative. It's implicit differentiation, but I need you to remember something important. I need you to remember all the rules that you've learned from before, particularly the product rule. Okay, you're still going to ddt both sides, right? ddt the left, ddt the right. We're not going to worry much about pi over 3. That's a constant multiple. We're not going to worry much about this either. That's dv dt. That's dv dt. This is pi over 3. Here's where we need to worry, right here. How do you take the derivative of r squared times h when r and h are both variables? I'm afraid we need the product rule. Here's your f, here's your g, and you should make a table. So f equals r squared is the first thing you're going to write. G is equal to h. Now I need f prime, and I need g prime. And what is f prime? F prime is a ddt on the r squared. And that's implicit differentiation, as is all of our related rate problems. Take the derivative normally. That would be 2r but the variables don't match, you will get a dr dt. Good, because we need one of those. G prime is a d dt on my h variable. I think you know what G prime would be. It's just dh dt all by itself. Also, product rule clearly states that the derivative is f prime g plus fg prime, right? So we have to do all that too. So let's wrap this up and let's see how all of these rates relate to each other. Now the left side, we've got that, it's dv dt. On the right side, we have a pi over 3 constant multiplier. But what we need to do is f prime g plus fg prime. Let's see if we can figure that out using our table here. So f prime g, let's start with f prime. F prime is right here. It's 2r, a dr dt, multiplied by g, which is right there, h. Plus, let's do f, which is up here, r squared, multiplied by g prime, which is a dh dt. Cleaning it up a little bit, we now know the way these rates or speeds are related to each other. Pi over 3, and this would be 2rh dr dt plus r squared dh dt. Very careful application of that product rule. I suppose you could do one more thing here. It's pi r over 3. You can factor out a common r there. It's one way to do it. So you can see that it can get much more involved if it's a product or a quotient or anything like that. Anytime you have a product of variables, you have to run the product rule. Even in this situation with related rates, all you need to do is make that table, and when you take your derivatives and the variables don't match, you must always put that singular extra derivative out there. That's it for related rates. I encourage you to really work on these. These can seem tough, but once you have worked through them a bit, you'll see that they're really not once you have the procedure. Oftentimes, dv dt, dr dt, all those others, they end up being numbers. Somebody will tell you dv dt equals 10 cubic centimeters per minute. They'll tell you what that number is, and they'll say, now solve for dr dt. Keep track of the units. Make sure the units make sense at the end of the problem also. Thanks very much.